All right, in this lesson, we're going to talk about our sinusoidal functions, our sine and our cosine functions, if we were to graph them on a coordinate plane. Okay, so it's important to note that our sinusoidal functions are periodic. So a function is periodic if there is a positive number c such that f of t plus c equals f of t. Okay, and that the smallest number c is called the period of a function. So all that means is that our function repeats itself over a particular interval, and the width of that interval is c. Okay, and it continues to repeat itself over and over and over again. Okay, so that period is the length of one complete cycle, okay, from beginning to end. The period of a sine and a cosine function for the parent function start off as 2 pi. So for every 2 pi, our function kind of repeats itself again. Okay, that's one wave or one period. Okay, for our tangent function, which we'll look at in our next unit, the period is just pi. Okay, so first off, let's look at our vertex form for a sine function. So f of x equals a times sine of b times x minus h plus k. Okay, where a, b, h, and k are constants, neither a or b is 0. So same form as the transformations we did for all of our other functions, from linear to quadratic to exponential, all those, it's the same form. It looks a little different though since we've got this sine function in there. Okay, and we can plug in a cosine as well, and it works the same way. Okay, to find the period of a sine function, then this b coefficient right in front of the x, but it's inside the sine function, we're going to use that to find our period. If we take the original period, 2 pi, and we divide it by the absolute value of that coefficient b, that'll give us the period of our function. Okay, and again, that's the length of one full cycle. So again, the period of sine of x and the period of cosine of x are both 2 pi. Okay, to find the frequency, which is directly related to the period of a function, the frequency is the number of complete cycles the wave completes in a unit interval. To find that algebraically, then we can take the reciprocal of our period. Okay, so the frequency of a given function is the absolute value of b over 2 pi. That's a b. Whew. All right, so let's graph these. Let's see what they look like. So I've got a little a nice graph here. I don't have any scale on it yet, so I want to give it some scale. Now we're going to primarily be graphing our trig functions where our x-axis is going to be our angle measure. So we're going to have angle measure theta, and it's going to be in radians, and our y-axis is whatever our function is. Okay, so if we start off with a sine curve, so let's say let's graph y equals sine of x. So we could say sine of x, or we could say sine of theta. You'll see it both ways. Okay, where the x or the theta is our angle, our independent variable. Okay, we want to start at the origin. So our sine function starts at the origin, 0, 0. And before we plot any other points, we want to give this a scale. So our y scale, maybe we'll go up 1, 2, 3, 4. We'll make 1 up there, and we'll go down -1 here. Okay, so we've got some space to work with on our y-axis. For our x-axis, the first thing I want to do is I want to find the period of this function. So the period of my parent function, like we just talked about, is 2 pi. So that's important when we find our scale. We want to find our period first. So I'm going to go out 2 pi. I want to make sure I go out 2 pi in both directions. So I might split that into fourths. Okay, so that tick mark is going to be 2 pi. So half of 2 pi is pi. Half of pi is pi over 2. and this tick mark is 3 pi over 2. All right, I'm going to do the same thing in the negative direction. So I've got negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. Okay, so now that I've got my scale, let's go ahead and graph it. We've got a point at the origin. At pi over 2, the sine of pi over 2 is 1. The sine of pi is 0. And you can look at your unit circle to check these measurements. The sine of 3 pi over 2, so think 270 degrees due south, is negative 1. And the sine of 2 pi gets us back to 0. So remember, this sine is a curve. So we don't want any sharp corners. We want a nice smooth curve. Okay, so that's one period of our sine function. So think about it kind of like a roller coaster ride. So we start here, we get on, and we go up, and then we go down to the valley, and then we come back up again, right back to where we got on the ride. Okay, and then if we were to continue to graph it, if we go out, let's go out one more period, then we would really be doing the exact same ride over again. So our next pi over 2 would be at 1, then we would be back at 0, down to negative 1, and then that would be 4 pi. This is 3 pi. Okay, back to 0. So then it would look the same again. All right, same thing with the negative direction. So we could literally, if we could on paper, take this and copy it over here, and it should be the same. Okay, same thing over here. That should line up right with every period of our function. Okay, but let's go ahead and graph it. So negative pi over 2, if you go in the clockwise direction on your unit circle, that's going to give you a sine or a y value at that point of negative 1. Negative pi is going to be 0, negative 3 pi over 2 is positive 1, and negative 2 pi back to 0. All right, so you can kind of see the pattern. It's going to give us the exact same piece as what we did from 0 to 2 pi. All right, and that would continue on in our negative x direction and our positive x direction to negative infinity and positive infinity. Okay, but we'll just graph 2 or 3 periods of it. Okay, so that's our sine function. Now, what if we graph our cosine function on the same graph? What's that going to look like? Okay, so y equals cosine of theta. Let's try that again. If we graph y equals cosine of theta. Now, cosine of theta starts with a y-intercept of 1. Okay, remember from unit 1 when we briefly looked at the sine and cosine functions, the main difference was that it started at 1, so the cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is negative 1. Again, you can pull these from your unit circle. Then we go all the way to 2 pi, and then we're back to our peak. We're back to our local max. So if we show that curve there, so there's one period of our cosine function. And again, if we wanted to graph this, we could continue on a couple more periods. What I might do just to show that it will be the same, then if I take that and I just copy it over here, okay, it's going to look like that. And then if we go into the negative direction, it should look something like that. Okay, so there's our sine function and our cosine function, the graphs of the parent functions for both. All right, so now let's look at some of the other transformations. All right, let's say we want to find the period of each of these functions. So we've got a couple of transformations going on. All right, so y equals negative 2 cosine of x over 3. For the period, we don't necessarily care about that. All we care about is what's inside here. So if I rewrite that, just the important part, and I want to factor out that 3 from the bottom, so that's really a 1/3 x. So our b value here is 1/3. Okay, so recall, and we're going to change that C to a B in both cases. That should have been a B. Recall that f of b times x is a horizontal shrink, and f of x over b is a horizontal stretch. So we're going to be stretching the period of our function. To find the period, we just take 2 pi, divide it by our b value. All right, in this case, we've got a fraction, so let's make 2 pi a fraction, and we're going to multiply it by its reciprocal. So our period is 6 pi for example number 1. All right, so it's got that horizontal stretch by a factor of 3. Okay, number 2, y equals cosine of negative 4x. Again, if we want to find the period, then we take 2 pi over, and we didn't do the absolute value here, we should have, but it was positive, so that didn't make any difference. But it will make a difference here. So we want to make sure that our period is a positive number. So this is really 2 pi over 4, which simplifies to pi over 2. So the period shrinks. We've got a horizontal shrink here by a factor of 4. So that period becomes pi over 2. All right, next up, amplitude of a sine function, or again, a cosine function would work just the same, is the absolute value of our a, our leading coefficient. Okay, so remember whenever we've got a times f of x, then that's a vertical stretch. So the amplitude is, if you look at the graph, is the height of the graph from the center of that function. Okay, so it's the height from the center. So if we look at these 3 examples, and we want to find the amplitude of each one, so we'll abbreviate amplitude like so. Amplitude is the absolute value of our a. So we can't see any coefficient there, but there's an imaginary 1. So the absolute value of 1 is 1. So the amplitude of our parent function is 1. So going back to our graph, note that the distance from the center of our function to its peak, that's our amplitude, and for our parent functions, that was exactly 1. Okay, so the actual distance from peak to trough, or from max to min, is twice the amplitude. All right. Y equals 1/4 sine of x. So to find the amplitude, we want to take the absolute value of that leading coefficient a. Since it's positive, it's just going to stay 1/4. So that would be a vertical shrink. Looking at number 3, we take our a value, which is -2. We take the absolute value of that, and we get a +2. So anytime we've got that negative, just like with any other function, that's going to flip it over the x-axis. But as far as our amplitude goes, since that's a measure of height, then it's got to be positive. Okay, so that would be a vertical stretch by a factor of 2. Okay, so kind of to summarize, our horizontal stretches and shrinks affect the period. We get that from our b value, and our vertical stretches and shrinks affect the amplitude, and we get that from our a value. All right, let's look at our other 2 modifiers. We've got an h and a k that we haven't talked about yet. So our horizontal shift, we're going to call a phase shift for trig functions. And vertical shift is still just a vertical shift. So the k on the end is still our vertical shift up and down, and our h value is still our horizontal shift right and left. All right, so let's kind of put all these together. Let's look at one example with a whole slew of different transformations. All right, we've got y equals -5 cosine of 3x plus pi over 6 plus 0.5. First thing we want to do is we want to get that into our standard form, or our transformation form. It's almost there, but note in our form, this b is kind of factored out of that expression there, so we want to factor out this 3 here. So what's going to happen? We're going to have same coefficient on the outside, and then on the inside we're going to factor out a 3. So 3 times x is 3x. And then we want to say, well, what can we multiply by 3 to get pi over 6? Because we're factoring a 3 out of that as well. So pull out a 3, we get pi over 18. 3 times pi over 18 is pi over 6. And then that doesn't affect our vertical shift on the end. Okay, so now we're in vertex form, or transformation form. We want to state the amplitude, period, phase shift, and vertical shift. So amplitude comes from the absolute value of our a variable. So our amplitude is 5. The period is our parent function's period over the absolute value of b. So to find our b value, that's the coefficient of our x. So that's 3. So we get 2 pi over the absolute value of 3. Absolute value of 3 is 3. So our period is 2 pi over 3. And our phase shift, we'll call that PS. We're going to shift to the left. So shift left pi over 18 units. And our vertical shift, we'll call that VS for short, for time's sake, is on the end there. Our K variable tells us we're going to shift up a half of a unit. Okay, so we'll practice these more in class tomorrow. As a little challenge, if you would write the sine and the cosine functions as a phase shift of each other. And on the following pages in your notes, there's a couple of example problems. Try this first page here that's got five graphs to sketch. Make sure you specify your scale, both your y and your x scale. Start with your parent function and then apply your transformations from there.